Good evening, ladies and gentlemen, and welcome to the Signal Hill Science Show. My name is Mike Daly, and today our guest is Dr. Terence Trico. Good evening, Dr. Trico.
Good evening, thank you.
Thank you for joining us today.
Thank you, glad to be here.
Great. So if you've been a regular visitor to the Signal Hill Science Show, you know that we have had the opportunity to talk about our night sky on a couple of different occasions. We've talked about astronomy, we've talked about the constellations, but what we want to talk about today is how we understand the night sky based on our new, on the computational progress that we've made over the last 50 or so years. It's almost unfathomable to think about the distances between planets and between stars and between galaxies and how big the universe actually is. So in order for us to get a better understanding of that, we have incorporated computers into the way that we interpret the data. Dr. Trico and I have had the opportunity to have a chat there fairly recently, and we've put together a little piece for you. While this piece is on, we certainly encourage you to write in with questions in the comments section below, and when we come back, myself and Dr. Trico will have a quick chat, and we'll be able to address those questions, and hopefully you enjoy the show. Without any further ado.
Hello there, and welcome to the Signal Hill Science Show. The Signal Hill Science Show is presented by Memorial University of Newfoundland's Johnson Geo Centre and the Faculty of Science, in partnership with Conference and Events Services at Memorial's Emira Innovation Exchange. Today, our guest is Dr. Terence Trico. Dr. Trico is a PhD from Monash University, which is, of course, in Melbourne, Australia, so all the way on the other side of the planet. He has postdoctoral fellowships, including at the University of Exeter and the Canadian Institute for Theoretical Astrophysics at the University of Toronto. He's presently the lead data scientist at Verafin and an adjunct faculty member of the Department of Computer Science at Memorial. Dr. Trico, thank you very much for joining us today.
Thank you, glad to be here.
Great. So today we're going to talk a little bit about space. In fact, we're going to talk about astronomy, and more specifically, how astronomy has evolved over the course of human history, and especially over the last century or so specifically. It's been a long, long time since humans have first set their gaze upon the planets and upon the stars and tried to figure out what they were there for and how we use them in our everyday lives. And of course, that has evolved tremendously, but never so much as it has since the advent of the computer, and especially the supercomputer, in making models of grander astrophysical events. But you can certainly tell us a little bit more about that than I can, so please, Dr. Trico, take it away.
Thank you. Yeah, so today I'm going to talk to you about the use of computers in astronomy. And computers have really revolutionized how astronomy is done. And when I talk about astronomy, I mean the scientific study of stars and planets and really everything else out in space, including really exotic objects like neutron stars and black holes, as well as the Big Bang and the history of the universe itself. So computers have become pervasive in our everyday lives. You know, you think of a phone or a tablet or a laptop or a gaming console like Switch or PlayStation. Those are some of the more obvious ones that are readily identifiable as computers. But there's also computers inside your car, or a light switch if you have a smart switch, or a smart thermostat, or really anything that has a digital component to it has a computer inside of it. So just as computers are embedded in our everyday lives, they've also become embedded throughout astronomy. Normally, when you think of astronomy, you think of looking through a telescope. And this is exactly what Galileo did 400 years ago in the 1600s. And I'm showing here a couple examples of telescopes used by Galileo himself. And what Galileo did is he used his telescopes to make observations of the moon, the sun, and the planets. Prior to this, people believed, for example, that the moon was perfectly smooth. However, when he looked through his telescope, he saw craters and mountains and all this structure on the surface of the moon that really transformed our view of these celestial objects. So just as telescopes transformed astronomy, computers nowadays are transforming astronomy once again. Much of astronomy is still done through telescopes, but the nature of telescopes have changed quite significantly. Here's an image of ALMA, the Atacama Large Millimeter Array, which is high in the mountains of Chile in South America. We can see that there's not just one telescope, but a field of telescopes. All these telescopes, all these dishes, they work in unison together to make a single observation. And this field of telescopes, they're powered by computers. Each dish records its image digitally, and they're combined together to make a unified image. A more extreme example of this is the Event Horizon Telescope, where you have not just a combination of dishes in one region, but you have a combination of observatories scattered throughout the whole globe, throughout the whole world, that work in unison to make a single observation. ALMA is part of that, as well as with telescopes in Mexico and Hawaii, in Europe, as well as in the South Pole and Antarctica. And what these telescopes were trying to image was a supermassive black hole at the center of a galaxy called M87. And we know that most galaxies have a supermassive black hole at their center. And in particular for M87, we knew the location of that supermassive black hole. We knew that because we could see this jet of material coming out of the center of the galaxy. And we knew that jet was powered by the supermassive black hole directly. So we could trace back the jet back to its base, back to the origin. And if we zoomed in towards that region, then we're able to try to image the black hole itself. And that's exactly what the Event Horizon Telescope was able to do by combining all these telescopes across the globe. And what I'm showing here is the image they were able to produce. Here we can see this bright ring of material, which is bright because it's really hot. And we have this dark patch in the center, which is the black hole itself. And it's black because it's a black hole. Black holes don't emit any light. They absorb and attract the light that's around them, which is why we can't see them. And that's why this region looks black. Now, to create this image, each observatory produced a massive amount of data. It produced about a petabyte of data each. And what is a petabyte? Well, if you think of the storage capacity of a phone, a petabyte is about 10 to 20,000 times that amount of data. And each observatory has this amount of data, and they want to combine that together to create their image. But they couldn't just send that over the internet because it's too large, it's too much. Instead, they had to physically put those data on a collection of hard drives and fly those hard drives all to one location to process that data. To get a sense of the scale of how much data that is, here's an image from their central repository in Germany. We can see rows upon rows of all these shelves and shelves of hard drives stacked on top of each other. And to combine all of this, you cannot just use a regular computer. Instead, you have to use a supercomputer, which has 10 to 100,000 times the power of a regular computer. So astronomy is not just changing the limits of, pushing the limits of telescopes, but they're also pushing the limits of computation and what computers can do. So computers have not just changed the nature of telescopes, but have also changed how we try to understand what we see out of telescopes. For example, here is a beautiful image of a spiral galaxy made with the Hubble Space Telescope. And a galaxy is a collection of billions of stars all in one region. And we can see here, each of these bright points is a star. And there are lots of questions when you get an image like this. We can see this spiral structure, these spiral arms coming out of the galaxy. How do you create this spiral structure? Where does it come from? And furthermore, how do you even create a galaxy like this? So as scientists, we create theories to try to answer these questions. And we want to run experiments to test our theories. But we can't test these experiments in a laboratory because we can't recreate a galaxy in a laboratory. So instead, we turn to computers to tackle some of these questions. So on a computer, we program the laws of physics, and then we run a simulation or an experiment. For example, I'm showing here an image made with the fire simulations of a galaxy that was created in those simulations. These simulations started with a small sort of baby galaxy and watched it grow and evolve over billions of years. And you can see the end result is a spiral galaxy that looks very realistic to the kind of galaxies that we see with our telescopes. And this image this simulation, it was produced on a supercomputer. This one in particular uses a computer about 10 to 100,000 times more powerful than a regular computer that ran continuously for a month or two. So it really is pushing the limits of what we can do with our computers currently as well. And this image is not just a pretty image that looks like a galaxy, but it's underpinned by the program that is recreating the laws of physics. It's a scientific recreation of a galaxy So we can make our scientific observations from that experiment that we run on our computer. But it's important that the simulation also accurately recreates that physics. For example, for my own research, I've looked at how stars are formed. And the general process for creating a star is fairly well understood in that you have a cloud of gas out in space, and that cloud of gas gravitationally collapses or condenses under its own gravitational weight until you form a star. Magnetic fields are thought to be important for that process in that they create jets of material that come out of a newly formed star or a protostar, just as we saw the jets coming out of a supermassive black hole. In my very first simulations, I programmed magnetic fields into my simulation, and I took that cloud of gas that was gravitationally collapsing, tried to produce a star in the center, but the magnetic field went completely haywire and it tore the cloud apart from the inside out. So I didn't do a very good job of recreating the physics on my computer. So I had to go and figure out how to add magnetic fields correctly. I had to go back and reprogram my simulations to faithfully recreate these physics. That took a lot of work, but the end result was I was able to rerun these simulations, rerun these experiments, have my cloud of gas collapsing down to create a star, and I was able to produce these jets of material coming out of the star that was formed. In the simulation, you can see this bright spot at the center is a star that was created, and you can see these jets of material coming out of the top and bottom of the star. So I thought I would also share a fun game that you can play yourself called Super Planet Crash. You can play this in your browser, and you have a star in the center, and you can just drop planets that orbit that star. You can drop planets the size of the Earth. You can drop larger planets, giant planets, even other stars, and watch them orbit the central star. And this browser game is like a scientific experiment itself because it's solving the equations for gravity, right? You have the gravitational attraction between the central star and the planet, but also between all the other planets as well. So if you have two planets that get too close together, they might collide with each other, gravitationally attract and collide with each other, or they might have a near miss and one might get ejected from the system altogether. So Mike, if you have questions.
I certainly do, and thank you very much. I mean, those are great slides, and it's such an amazing topic because we know so much, but yet we know so little. In the sense that we keep creating these simulations, we keep looking outwards towards the stars, and yet every time I turn around, I feel like we're getting surprised by something. There's some celestial body out there that's acting in a way that we don't expect it to, and of course, there's very likely some external events that are happening in that particular system or in that particular galaxy that lead to that. But as you come across these unknowns and as you come across these differences that sort of throw themselves into the face of physics as we know it, what changes? Does our understanding of physics change, or does our understanding of the model change? And do we feel like we've lost something or we've missed a step or a calculation, in regards to how galaxies are formed or how they interact with each other?
Yeah, really, it's both. Both our understanding of physics changes and our understanding of the universe can change. There are these observations of black holes and neutron stars where they really push the limits of physics. And so we have to run our numerical experiments on a computer, we can't create the environment of a neutron star in a laboratory. So as we understand these objects further, they help us refine our physics understanding in these really extreme environments. And then just the nature of the universe as well, we have these observations. It's becoming more clear recently that our measurements of the age of the universe are slightly in disagreement with each other. So now we're starting to question exactly just how old the universe is. And so it's really, every time we make a new observation or a new measurement, we try to answer a particular question, but then that just raises a whole host of other questions.
And because we look at physics and mathematics as a universal language, we always feel like, it applies to everything in the known universe. So to all those budding scientists out there in the high school and junior high age that are hopefully watching this broadcast right now, they have an opportunity, and you can tell me if I'm wrong, they have an opportunity not just to discover new things about the natural universe, but to find out new aspects of science and stretch our understanding of what physics is in the natural world. Is that true?
Yeah, absolutely.
Awesome.
Just talking about my own path through school, I was really interested in physics, and I was really interested in computer science. And nowadays, those two merge together fantastically. It's very hard to do physics or astronomy without having some experience in computer science. And there's a whole realm of possibilities that, and questions out there to answer, that if you wanted to go into sciences, there's lots of room for you to answer those questions.
We in the description below, for anyone who's had a chance to watch the video and hopefully have a chance to look at this beforehand, we do have the link to the super planets experiment that you talked about online. I had a chance to try it myself a couple of times, and I did indeed crash my planets more than once, but I think that's part of the fun, and I think that's part of the understanding of how things work. Right now you'll look behind me, and I'm at the Johnson Geo Center, and up in our ceiling we've got representations of all the planets, but right now I think we're able to look at Saturn, Neptune, and Uranus, if I'm not mistaken, they're behind us. These are these ones behind me are gas giants, and of course they exist more on the outer sections of our solar system. And you can always, you're the expert, you can correct me if I'm wrong.
No, you're right.
But when we look at this, when we look at the different masses of these planets, and as we put them into the super planet experiment that we had there, that we have listed below, explain a little bit to folks about how we are able to maintain the same gravitational pulls for all of these planets, and they stay in the fairly similar orbits. Is it a delicate balance, or is it a grind that eventually creates this type of system?
Yeah, I mean, if you play Super Planet Crash, you're only simulating 500 years, whereas our solar system has been around for 4 billion years, right? And we have these planets that maintain their orbits. They don't crash at all. And part of that is a little bit of selection bias in terms of if the planets were to crash, then they wouldn't be here for us to see them, But it's a very fine balancing act between the gravitational attraction of all these different planets. And they're spaced, far enough apart at just the right amounts that they don't tug on each other too much. You do get some effect from this, but not enough to actually pull them out of their orbits, so they stay stable.
And would you think that the size and the shape and the orbit of these planets was dictated by the various gravitational pulls that happened throughout the formation of our particular solar system?
Yeah, and actually there's a very good example of an exoplanetary system called TRAPPIST. They have 7 or 8 planets that are in very, very close proximity to their host star. And they manage to stay in stable orbits with each other because they're in resonance with each other. For every time the central one makes an orbit around twice, the next one makes 3 times its orbit. The next one goes 5 and then 7 and so on. And because they have this very nice resonance, they're able to stay in that stable orbit. If they were ever off by a little bit, then over time they would end up colliding with each other.
When we look at all the models, especially that the supercomputers are able to offer us for our known universe, when we observe the night sky, we're seeing light from sometimes millions, sometimes billions of years ago. The models that we're creating now with the supercomputers, are they able to sort of give us real-time updates on where those galaxies might be at this moment in time?
Yeah, and I mean, that's the fire simulations I showed. Part of that was they start off at the very early universe, and they evolve those galaxies to present day and try to see what those galaxies are like now. So there's the whole range of timescales that you can look at. In a simulation, you could simulate the very early universe. You could simulate how it is today. In terms of real time, we have a running joke of you can simulate something in real time, but how quickly a galaxy changes, it changes over billions of years. So if you watch it in real time, it's not really going to change that quickly. So the point of the value of these simulations is that you can simulate those billions of years within just a few weeks of real time.
Which is, it's incredibly amazing. You see statistical representations of graphs over, when we talk about human life, decades and centuries. But then you look at them when they're really compressed, and you can get a real sense of evolution and how things change. It might not feel quickly, but it is. It can be an awfully quick process. What is the benefit to us here on Earth of being able to create these simulations and be able to really gain a deeper understanding of what goes on outside of our solar system?
Well, the telescopes and the simulations that are run in astronomy, they're really pushing the limits of computers. And it's really driving computer science forward in that sense. The square kilometer array, it's being built in Australia. The amount of data that that is going to produce, it's literally a square kilometer of telescopes, similar to what I showed for ALMA. And the amount of data that that will produce, it's not even clear how they're going to collect all that data and store it and process it. So it's really innovating, the infrastructure and the technology to be able to power these telescopes to try to create the observations that scientists want to do.
One last question. You've been around this field for quite a while now, and you've certainly gotten your hands wet and your feet wet and your hands dirty. Is there one particular discovery that's happened during your career that has really excited you about this particular field?
There's been, I think, a few. I mean, not directly in my field, but CERN several years ago made the observation and discovery of the Higgs boson. Mm-hmm. That had been a theory that had been predicted for 50 years. And then to finally make that measurement and confirm that it was true, that was really revolutionary. And the Event Horizon Telescope, which I showed in my slides, being able to see a black hole. Black holes have been predicted by Einstein's theories from 100 years ago. And it was a contentious topic at the time of, how could you have something so extreme and so bizarre? And then it's only the past few decades that we started to accept, okay, there are supermassive black holes. There are stellar mass black holes. We have an idea of how stellar mass black holes might form from, the supernova of a giant star. It's still not clear how a supermassive black hole is formed, but now the Event Horizon Telescope has directly seen one of these. So it's not just circumstantial evidence that they exist, but here's a direct image of one. And I think that's going to change things quite a lot over the next few years.
It's pretty amazing. Those two examples that you gave, the Higgs boson particle as well as the black holes, it must feel wonderful to be a physicist and finally to see those things observed and say, yes, we were right, and so that really backs up our physical view of, our scientific view of the physics of the universe. So it lets us know that we're on the right track, and hopefully that can only grow, but there is a certain comfort in that, knowing that we're going in the right direction, I guess. Hey, Terence?
Yeah, that's right. It's great to see the theories that you create, have them come true, and the predictions you make, have them come true in the end.
There you go. So I don't know if there's anything that you wanted to add or any other anything else you wanted to say or share?
I guess one other thing that I was thinking of is LIGO, the Laser Interferometer Gravitational Wave Observatory, as another example of something that's revolutionizing astronomy. That has made huge impacts over a number of fields. In terms of what the observatory does is it measures gravitational waves. So you have two black holes that are spiraling in together and they collide and make one gigantic black hole. It sends out ripples throughout space, and these observatories measure these ripples. And so they've seen dozens of black hole mergers now. And a few years ago, when I was at the University of Toronto, they saw this black hole gravitational wave signature. Well, it wasn't a black hole, but they saw this gravitational wave signature come in, and it was from two neutron stars that had collided. And everybody in the world instantly pointed the telescope towards that location, and they saw the supernova coming out of that, or the kilonova coming out of that. And it completely changed. We saw kilonova before, but we didn't quite understand what they were. But then with the Gravitational Wave Observatory, we had clear evidence. This is what this event is. And then we could had all these telescopes looking at it. It really revolutionized not just understanding of neutron stars, what these kilonova were, but also it was a very good experiment understanding for understanding nuclear physics, because it created all sorts of heavier elements like gold and platinum. And we understood now that all of these heavy elements are seeded by these type of events throughout the universe. So it really was a transformative observation.
And it goes back to the rumor that I've been hearing that we might actually be starting to mine comets before too long because of all the rich minerals and heavy elements that we cherish so much that are readily available apparently in these celestial bodies. So it'll be an interesting times coming up, I think.
Yeah.
All right. Well, Dr. Tricco, thank you so much. Ladies and gentlemen, our guest today has been Dr. Terence Tricco, and this has been the Signal Hill Science Show. lots of information here, and if you haven't had the opportunity, please check out the links in the description below. It'll just probably lead you down a wonderful rabbit hole of science and exploration, and we wish you all nothing but the best of luck with what comes next. Thanks, Dr. Tricko. Thanks, everybody.
Thanks for having
Bye.
me.
And there you have it. That was a lot of fun, Dr. Tricko. This has quickly become one of my favorite subjects. When we talk about astronomy, our solar system, the grander universe beyond, I've been just so intrigued by it. So this is a lot of fun for me, and I'm really glad that you took the time to be on our show. Now, we did have some questions come in, but I'm going to ask my own question first. We talked on this a little bit, but I want to make sure that everybody who's watching is aware of some of the things that we chatted about. We touched on supercomputers. What exactly is a supercomputer?
Right, that's a really great question. You know, when you think of a supercomputer, you kind of go towards something science fiction, but supercomputers are real, and they're really not that abnormal or really fantastical in any way. The top supercomputers in the world they might have some specialized hardware in them, but a lot of supercomputers are really just built out of off-the-shelf like components that you could go to Best Buy or some other hardware store or computer hardware store and buy. And really it's just your regular sort of processor, memory, hard drives that you'd have in your laptop or your computer. But rather than just having one of those things, it's say 10,000 or 100,000 or even 1,000,000 of them all linked together, and then they all work in unison together to crunch numbers and do a simulation. So the supercomputer side of it is just having all these computers working in unison.
So, I remember seeing a lot of these comparisons of what computers looked like in the 50s and the 60s and what, huge, they would take up this space well beyond,
Yes.
and what they've become now in our hands, the computational power that we can actually hold in our hands. When we look at what's going on out there today, like what are some of the largest supercomputers in the world?
Well, I showed one of the largest supercomputers in the slides. That is Summit, which is at Oak Ridge National Labs in the US. That is currently the #2 computer. And you can see, if you, in that image, you could see that really took up the whole room. It's because when you have 100,000 computers all working together, even if they're the size of, say, your laptop, but you have 100,000 of them, they're going to take up a full room. So there's a large number of challenges, actually, to run a supercomputer, because if you have your laptop and you're watching a movie or playing a game, you can feel your laptop heat up. A supercomputer will heat up 100,000 times more so. So you have to have a lot of cooling and specialized systems in place to be able to run a supercomputer. In terms of the largest supercomputers in the world, it's a little bit of a supercomputing arms race right now. Maybe 10, 20 years ago, say every university might have their own supercomputing cluster, whereas nowadays supercomputer is getting so powerful that it can no longer be done with a single university. So they're really becoming national projects. The #1 computer in the world is in Japan. It's supercomputer Fugaku, which is about 2.5 times more powerful than Summit, which is at Oak Ridge National Lab, and that is built by the Department of Energy. And then after that, it's one of the Chinese supercomputers. And then the list goes on from there.
And we talk about how these are national projects, and I wonder, are there supercomputers being built by the private sector right now?
Sure. Yeah, you think of Google.
Sure.
They had a project where they were trying to solve this heating problem with their supercomputers by putting them in big bunkers and putting them down in the ocean, because then you have all this cool ocean water just surrounding it to try to keep it cool.
Yeah.
So they're trying to do some pretty innovative things these days.
Neat.
Yeah.
Yeah. And again, like I said, this has just become one of my favorite subjects. I could be selfish and talk and ask and ask. However, we've got some questions from our viewers, and thank you very much for tuning in, and thank you very much for your questions. Mirik would like to know, how commonly are GPUs used in astronomy simulations? And of course, while we do ask that question, if you could define what a GPU is.
Of course. So a GPU is a graphics processing unit. Your computer has a CPU, a computing processing unit, and a lot of them also have GPUs. And GPUs are certainly well known by like PC gamers who want to run the latest video games on their computer. They want to have really great graphics. And part of because of gamers, the graphics cards that have GPUs on them, they become really affordable. right? The cost for the computing power you get out of one of those is much more affordable than getting the really high-end CPUs. So there are a lot of supercomputers nowadays that are really incorporating GPUs as part of them. Summit is an example. About 2/3 of its computational power comes from GPUs. It's a real programming challenge to, if you have a program that you've been using for 10, 20 years to do simulations, and it's been built to use regular CPUs, and then you have this different architecture of a graphics card and a graphics processing unit, it can take a lot of work to try to translate your code over to using that. So I don't think we're going to see a complete shift over to GPUs in the future, but I think they'll end up as complementing the current computational landscape.
Okay, brilliant. Another question from Eric here. We talk about, this is a lot of data entry. We have to input all this data in order for these computers to do their work. We have to use our observational data. However, Merrick would like to know how were you using artificial intelligence in your scientific work, and is AI commonly used in astronomy?
Well, it's starting to become more common for sure. When you think of artificial intelligence, it means different things to different people. For some people, artificial intelligence just means the computer doing anything that's kind of smart. So in that sense, computers have been doing AI for a long time. They do smart things all the time. Nowadays, and you might have heard of the term machine learning, there's been a real boom in that in the past 5-10 years. Certainly Google and Facebook and the other top businesses, they use machine learning all over the place to solve tons of their problems. Some people are trying to figure out how to use machine learning in astronomy. And when I was at the University of Toronto, there were a couple of PhD students, graduate students there, who were using machine learning to try to solve the problem they had in a more efficient way. But the problem with machine learning, and I guess AI in some sense, is that it can be really hard to understand what the computer did. Like when you're doing a scientific simulation, okay, here are my inputs, here's the process it went through to create the simulation and get an outcome. And then you can work back and make discoveries from that because you understand how things worked. But with AI and machine learning, you don't always know what's going on between your input and what you've produced at the end. So it's hard to make inference about what was really important or exactly what was to try to make discoveries out of that can be a real challenge. So it has its place, but scientists in general are still trying to figure out how to use AI and machine learning in the right way.
Sure, and we see it a lot actually. The media, it's probably not a great place to look for your information all the time, but AI has been painted in sort of a negative light in a lot of senses. We see the nefarious purposes that it has. We always think about Big Brother watching us and how everything's being computed in some deep dark laboratory somewhere. But in addition to the observations that we're making from Earth, AI is actually playing a huge role in space exploration. So as we continue to send satellites and larger ships beyond our solar system or into our solar system and beyond, we're talking about self-replicating machines, things that are able to look at the environment that they're in. Have you touched on any of this and recreate themselves and use things from their environment? Have you touched on any of that kind of, have you noticed any of that kind of stuff in your work?
Not directly, not directly in the stuff that I do. I'm very much focused on, running a simulation, taking the laws of physics, recreating that on a computer. Whereas if you are getting into self-replicating machines, that's kind of an engineering type of problem. I know there've been talk about, we could mine asteroids and things like this, but I think that's still pretty far distant in the future.
Yeah, well, dare we dream, right?
Yeah.
Speaking of simulations, I've got a question here from Jeremy. Jeremy would like to know, are the computer simulations you talked about used for hypothesis testing or hypothesis generation, or perhaps both?
Definitely both. Oftentimes it starts off with, I have an idea of I want to test this hypothesis. So to give an example, in the simulations I showed, where I was trying to create a star and we had this jet of material that was coming out of the top and bottom of it that was generated by the magnetic fields, we want to understand, well, how important are the magnetic fields? We have a hypothesis. Well, it's both the hypothesis and the exploration. We want to understand, you can pose a question and try to see the answer to that. And sometimes it's, okay, this is kind of important. Let's just explore. Let's just try a bunch of different combinations. And then we'll get a sense of, this part's maybe more important than this one, or So it really generates answers, but also you can go and get more questions out of it too.
Which is why I think the Planet Crash game that we had is so invaluable, especially for these young budding scientists. I mean, these are simulations that are very simplistic in nature, but can lead to so many other questions. So, I mean, kids, if you have a chance to look at some of to try this game, I highly recommend it. It is a lot of fun. I'm sure you'll do better than I did at it, but that's part of it. Like I said, crashing these, it's going to lead you to more questions, and questions are exactly what we're trying to gear people's towards.
Yeah, and if I can expand on that,
Sure.
the Super Planet Crash, that game, it's, you have a star and you have planets going around it, and you want to just drop planets in and see, do they stay stable over the course of the game? And it's really no different than what a lot of scientists do with their simulations. They solve the equations of gravity and they put a bunch of planets in, and they want to understand, okay, how are these stable configurations of these planets? So you can do a lot of science even with something relatively simple that looks really fun, but you get a lot of science value out of it.
And I don't want to discount it by saying it's a rudimentary type of simulation. I mean, it is obviously, there's a lot of calculations, and it's great that it's already done for you kids to jump in and try. But when we do talk about simulations, what are some of the largest simulations that are being performed in astronomy right now?
Right. So, when you think of a supercomputer, that certainly allows you to make really large simulations. You can compute a lot on a supercomputer. So one of the largest simulations that I know of is the illustrious TNG, which is the next generation. There was an original illustrious maybe about 7 years ago, and then they followed it up with the next version of that maybe about 2 years ago. And that simulation, it took 130 million CPU hours, so hours computing on the CPU, which would take, on a single computer, would take about 15,000 years to accomplish. But because of the supercomputer and they have 100,000 or more computers working together, they did that in only 2 years.
Amazing. And like these simulations, how you talk about all these computer hours that go into it. What are some of the biggest challenges in creating these simulations?
Yeah, it looks kind of deceptively simple. Like if you watch a movie, for example, and there's a scene with some water flowing, you can look at that and recognize, okay, that's like a digital scene. That water was recreated. That's not real water. But it might look really realistic, but that scene doesn't necessarily mean that it's actually recreating physics. Like there's a set of equations that describe fluid motion, which are the Navier-Stokes equations. And these are the type of equations that are applicable for any sort of fluid, like water, even the air around us, the coffee in your coffee cup, as well as gas out in space, or the sun is made up of gas, which you can solve with these equations. So the type of simulations that we do, we solve these equations to create something that is realistic, that the result that you get out of, you can make a scientific analysis of it. Same as if you had a tank of water in a laboratory and you made some measurements out of that, you can run an experiment or run a simulation on your computer, make measurements out of that, and they'll be scientifically valid. So it's a slight difference from what you might see in like a movie. Some of the challenges, just to talk about my own research, myself and my collaborators, we were doing simulations of water that has dust in it. So a very simple level, if you think like of a river flowing, it's going to drag pebbles along with it. So the equations for doing this are kind of simple in some sense. You have water moving and it just pulls the dust along with it. If you solve that on a computer, it turns out that if you just solve those equations very straightforwardly, it'll work beautifully for large like pebbles, or if you have like a very high moving river, you can push boulders along, works great for that. But if you have like very fine silt or dust, it becomes really computationally challenging to actually simulate that aspect of it. So one thing that we've done to try to counteract that is you can play you can play with the mathematics, you can play with the equations. You can sort of juggle them around and rearrange the mathematics so that the mathematics is identical, but when you solve that on a computer, it has very different computational properties. So we have a new method where now that works extremely well based on this reformulation of the mathematics, works extremely well for this very fine, silty dust, but performs terribly for large boulders. So we're trying to put the two together to bridge the large stuff and the small stuff. in a computational way. So it can be really challenging. Something that might look very intuitive, very simple to do, can be actually quite challenging to recreate faithfully on a computer.
So it sounds like it's an ever-evolving discipline, and there's still lots to learn. And that's
Absolutely.
something we love to promote here on the Signal Hill Science Show, is just reminding all you kids, we don't know everything. And so we're counting on you to come up behind us and answer a lot of these questions and keep this good work up. I have a question here from Jeremy. What kind of computer did you use for your research that you showed us? Was part of our pre-recorded piece. Was it like a laptop or a big computer at a university that you had to connect to?
I've used several different supercomputers. Nothing has been run on my laptop. I've used sort of over the years. I did my degree in Australia, so I was using some of the infrastructure down there. As well as when I was at the University of Toronto, I was using actually a supercomputer that was local to the University of Toronto. But just talking about the computational landscape, here in Canada, we have a national computational infrastructure, which is sort of pulled together all the different areas. They used to have sort of regional areas of Atlantic Canada, Western Canada, Central Canada. Now that's all been unified just because of the scale of supercomputers have grown so much. So nowadays, I'm using the national infrastructure.
Okay, so you've got access to a big grid, big system.
Yeah.
Yeah, and because these are big computations. If you had your druthers right now, is there a new simulation that you'd like to create?
So yes, I have a few things that I look at. I'm very interested in the trying to make these programs to run these simulations. And sometimes you have to do very basic kind of science to validate that your code works correctly. You don't just create your code, program it up, and then jump to trying to create a star or simulate a galaxy. You want to validate that it works correctly first. So I've been doing some simulations of different basic hydrodynamic phenomenon. One is the Kelvin-Helmholtz instability, where you have two fluids that are moving past each other, and just by virtue of moving past each other, they start to mix with each other, and it creates turbulence. And turbulence is sort of ubiquitous throughout every fluid, and it's an area that I've spent a lot of time researching too.
What do you think is some of the bigger impetus that have pushed this science forward? I hate to say it, but it feels to me, in some weird sense, that video games and their evolution and the desire to have as realistic images as possible, and of course that spills over into CGI for movies, this seems to be, there's a lot of money in Hollywood, and it seems to drive that sort of idea forward. So if we talk about the chicken and the egg, is it astronomy and astrophysics that sort of pushed this field forward, or was it more of the entertainment value that came from regular everyday viewing and playing?
I think they're a little bit distinct. They're both driving it forward. They're slightly distinct in like Hollywood, they'll have their own computers. They'll have their own supercomputers, their own hardware to do this. And it's not just astronomy and astrophysics that are pushing computers forward. It's really all of science.
Sure.
Like all of science is moving towards massive simulations. And the fire simulations I showed, where you had a picture of a galaxy to try to recreate that image of what Hubble's seen. There's a lot that goes into those kind of simulations, right? You have the fluid dynamics, you have the universe itself changing over time. You have stars that are forming, stars that then go supernova and they explode out. You have magnetic fields, you could have dust in there. The stars emit light and heat, and they could change the properties of the gas around it. There's a ton of different things that go into a simulation like that.
Yeah. Just for our younger viewers, if you think that this science doesn't apply to you, it does. You see it in your everyday lives, and of course, these simulations are going to be invaluable in how we treat our planet and our solar system and our universe, because we are, whether we like it or not, moving outwards from this planet and exploring more and more and farther and farther. So it's going to become increasingly important for everybody's lives. And I think it's going to happen fairly quickly,
Yeah.
And so these simulations, the more mature that they get, the more information that we get, and the more we can plan and make better choices for our future.
Absolutely, and you can think of climate change as an example of that.
Huge example.
Right? People are trying to run simulations of the whole planet to understand, because climate change is a global problem. They want to run simulations, and really they're running fluid simulations very similar to what I do, just in a different application. And they're pushing the limits of computation too, right? They're trying to make these massive simulations that take the top computers like Summit and run them, to their entirety at peak efficiency.
We always give everyone the opportunity. Is there anything else you'd like to add? Any personal notes that you want to share with everybody?
No, I think I'm good.
Yeah, and I could, like I said, I could ask questions. We could be here all night, but then we wouldn't be able to have you back again. And we certainly would love for that to happen.
Yeah, that'd be great.
Awesome. So again, thank you very much, Dr. Terence Trico. Our producer this evening is John Duff. We're here at the Mirror Innovation Exchange. My name is Mike Daly. Thank you very much for tuning into the Signal Hill Science Show. Keep asking questions and keep learning.
Thank you.